So yeah, I'm bringing up the back of the train here for the New Mexico State group. I work in collaboration with my advisor, Dr. Chris Churchill, Glenn Kapsad, Vicki Nielsen, Sebastian Joe Gomez, and then two collaborators from Penn State, Jay Charleston and Sal Gavin. So what I'm going to be talking to you about is I did a study and I've figured out that there might be a very strong mass dependence when you're looking at the kinematics of gas-around galaxies. So the first thing is just to paint a nice picture of what we're trying to do. We need to figure out the origin, the lifetime, the life cycle of gas-around galaxies in order to figure out how they evolve. It's not as simple as just pinpointing what might be outflowing, what might be inflowing. We're also trying to figure out exactly what type of gas is participating in each of the processes that go into making galaxies we see today. Building a worthy sample involves a lot of things in order to try to get all of the properties of the galaxy and all the properties of the gas in order to measure everything accurately. And so that involves galaxy imaging, good resolution images so that you can model the galaxy properties themselves, and good galaxy redshifts so that you can pinpoint where in velocity space some of these absorption features might lie around the galaxy. We also need really high resolution spectra, and so I'm going to be looking at costs to try and get some good ultraviolet data on these galaxies. The picture below is just a great picture of the Magellanic Stream. It tells you that when you're looking at a galaxy, there's a lot more going on just in a small region around it than you might be able to see from either imaging or spectra, things like that. And so what I've put together, we have a great series of Hubble images. This is all archival data that I'm going to be showing you. We have images of the fields of quasars, which have been spectroscopically observed with COS. And in those fields, we have identified the galaxies and gotten the redshifts and that type of thing. Each of the galaxies you see here are these little postage stamp pictures of the galaxies with the arrows pointing towards the quasar. And so we're able to locate not only the position on the sky, the orientation with respect to the line of sight of the quasar we're observing, along with the impact parameter. Below the COS spectra, I picked out these. They cover, all of them have line alpha, line beta, and the oxygen 6 doublet observed as a requirement of the sample. On each of the spectra, we're able to do void profile fitting, and on each of the images themselves, we can model the galaxy in kind of the flowchart process that I've got back here. And so we first model them, and this allows us to get not only the galaxy halo mass itself through halo abundance matching, but also the on-sky orientations with respect to the quasar line of sight and the inclinations on the sky to figure out where geometrically this gas that we're observing in the quasar spectra lies. The next step is void profile analysis, and so what we're able to pull out from there are the column densities, the Doppler B parameters, and the individual component velocities that we're going to be looking at for these hydrogen clouds. And finally, we get to relate the galaxy and the absorption properties and try to figure out a really good 2D picture of where this gas is, and using the velocity components, how that gas might be moving with respect to the galaxy. The 2D picture looks kind of like this. This is a plot from my most recent paper. We actually scale the impact parameters by the virial radii of the galaxies because we're looking at a large mass range to try to get a uniform picture of what we're seeing here. You guys might not be able to see the back, but the galaxy little diagram is in the lower left of the plot. But what happens here is that the y-axis corresponds to the minor axis of the galaxy, and the x-axis corresponds to the major axis. And so we actually have a full 2D picture here with dotted lines being different virial radii, 1, 2, and 3. With regard to the impact parameter. The points are color coded by the hydrogen column density. We actually have a relatively small sample, 14 galaxies at the end of the day. This ended up showing simple hints of the highest column density H1 absorbers lying along the major and minor axes, but it's only 2 data points. The most interesting thing that comes out of this is when we start looking at the gas kinematics. Like I told you, we've got good, we have 30 kilometers per second precision actually in the galaxy redshifts. We've got really good component velocities for the void profile fitting in the COS spectra. And this is a difference between the cloud velocities we measure and the galaxy's systemic velocity as a function of the halo mass of that galaxy. We span a range between somewhere about 10 to the 10.5 to up to 10 to the 12.2 in halo mass. And the colored lines correspond to the theoretical escape velocities of these individual galaxies as a function of the mass, and also at different functions of d over r meter, so for escape velocity at different distances. You can calculate and compare the same colored data points to same colored lines to try to determine if that gas is moving greater than or less than the escape velocity of the halo. And we can actually do that really simply by just dividing that delta V, the difference between the cloud velocities and the galaxy's aesthetic, by the escape velocity of the halo. What you find is there seems to be some type of trend going towards from low mass to high mass with a decreasing amount of gas that's moving at greater than the escape velocity of the halo. And so we just look at them between high and low mass galaxies, and we consider how much of that gas, if it's moving greater than the escape velocity of the halo, might eventually escape into the IGM around that galaxy. We find that there's a greater escape fraction around the low mass galaxies than there are amongst the high mass galaxies. In fact, at greater than about 10 to the 12 solar masses in halo mass, we don't see any H1 clouds moving faster than the escape velocity.
Sorry, how were the halo masses and escape velocities done?
So the masses were done from halo abundance matching, and the escape velocities were just calculated at the impact parameters, so it's kind of a conservative limit on the escape velocity.
And the squares are beyond how many? I can't see from the back.
What is that?
The red squares are how many Vero radii away?
Oh, so the red squares are 0 argers greater than 2. And the light blue, 0 arger less than 1, and then in between are the green triangles. So we're kind of coining the term differential kinematics here in the context of the SPH simulation paper by Ben Oppenheimer describing differential wind recycling. In that paper you described where in lower mass halos, or at higher mass halos, you had a higher frequency of outflows going up into the halo and then falling and raining back down. And so actually here we have in the higher mass halos, we see the gas can't escape the potential. The mass of the galaxy seems to be determining almost all the properties that might come about as a result of outflow and inflow interplay. And we find that the fraction of bound H1 absorbing clouds decreases as you get further away from the galaxy, which is to be expected. We also, of course, do find that as halo mass decreases at all radii, the number of clouds that might be able to escape the galaxy increase. And so we want to kind of try to figure out what this could mean in the context of inflow and outflow gas and figuring out what implications this might have in the galaxy evolution. With the help of Sebastian Trio Gomez, we were able to look at a simulation of a galaxy that he did. It's about 2 times 10 to the 11 solar masses in halo mass. What he was able to look at was the radial velocity of the gas relative to the galaxy at different distances from the galaxy. The blue curves are the circular velocity, and the green curve is the escape velocity of the galaxy itself. Negative velocities towards the bottom correspond to infall, and then positive velocities are outflow. We find that the infalling gas rarely, if ever, exceeds the escape velocity of the galaxy. However, when you look at the outflows, all the positive velocities actually have the ability to see gas moving at greater than the escape velocity associated with this galaxy. And so, when I say that the delta V over V escape gas is associated with our lower mass galaxies, it traces outflows, it most likely does. It might not be 100% true, but when we're seeing this gas moving at these velocities, we can start to assume that most of it is outflowing. Taking that step forward, we can really start to think about what theoretical implications this has in galaxy evolution. And so this is the stellar mass to halo mass relation from Barisi et al. 2010. And there's a distinctive turnover in the slope, occurring about a little less than halo masses at 10 to the 12 solar masses. And in my sample, it actually becomes a natural divide between galaxies that expel most of their gas in outflows, and then galaxies which really try to hold on to most of their gas. And so, with the escaping outflows into the IGM happening in the lower mass halos, it's strange that this happens at the exact same point. And you can kind of think about it, with these higher mass galaxies holding on to their gas, that the metals might be allowed to stay in the gas or in the galaxy really preferentially, whereas the buildup of the stellar mass in these lower mass galaxies having to come from mostly more inflow than outflow. It is actually transferred directly into the Mass-Metallicity Relationship, I should say the ISM Metallicity Relationship in galaxies. This is a Tremonti et al. 2004 result where he measures the gas phase metallicity in galaxies as a function of the stellar mass of the galaxy. I converted the halo masses I found in stellar mass and found that the change in the slope of this mass-metallicity relationship occurs at almost the exact same point where I find that the galaxies, the high-mass galaxies, have no escape fraction gas. And so this is a completely logical explanation to figure out why mass-metallicity relationship turns over. And that's that at lower masses, the outflows can escape into the IGM. The metals actually leave their galaxy and they aren't used in the star formation of the future. When you start holding on to almost all of your gas, the outflows remain in the host halo and might eventually be more likely to rain back down and participate in star formation. And so it just falls naturally out of the kinematics, which are governed almost exclusively by the potential of the host halo. And so my conclusion, the fraction of H1 clouds which could escape their halo does increase with increasing distance from the galaxy. This is natural. However, in low mass galaxies, at every V over RV, at every scaled impact parameter, low mass galaxies have a higher fraction of observed escaping H1 gas. The low mass galaxies expelling more of the gas seems to be tied, or at least a very important anchor point when looking at the galaxy evolution of the galaxy when it comes to the interplay of inflowing gas, outflowing gas, and the star formation, the way it goes about as a result of this. And so overall, I would say that galaxy mass seems to be one of the most important things you can possibly think of when describing how a galaxy is going to grow and evolve.
So we can have some questions for Nigel, and then I think we can just go into a general discussion.
Yeah, trying to drive your key result with Raman Borla's recent work on dwarf galaxies, where he's focused on carbon-4 instead of H1, which may tell a different story. But argues that very little of the gas is traveling at a speed above the escape velocity.
That's Cosworth's result. Yeah. And so the carbon 4 does seem to be a bit of a different beast than the H1, that's for sure. But I'm not sure.
I'll caution you that when we do it with H1, I bet we'll get the same result.
Probably. I don't know if it's a sample selection thing or if it's just a coincidence or a type of analysis we're doing.
I agree with everything you say about the green outflows and so on. We pointed out earlier this year, in a paper by Simon Beale, we'll talk about this more tomorrow, that there's this curious coincidence, in our view, a curious coincidence, that quenching, which is that turnover, occurs just as galaxies are getting their act together and are really starting to form a large fraction of their baryons into stars. People often say galaxies are so inefficient. The galaxies at the peak of that curve are really doing very well in turning baryons into stars. And I think this, and that also is why the mass-metallicity relation turns over. It's a reflection of that same efficiency. And so this mechanism, that it's at that halo mass that the winds are no longer getting out, but are then just heating up the halo and pressurizing it and essentially cutting off the accretion, right, causing the quenching, I think is a very attractive explanation of what otherwise is a bit of a coincidence of why quenching occurs just as the internal efficiency of galaxies is getting up towards the theoretical limit of barrier. So Simon will talk more about that tomorrow.
I agree.
So, this seems like a pretty nice interpretation of the data. What I'm trying to understand, so Peter Ruzi a while ago reminded me that as you go lower and lower in galaxy mass, the fraction of those that are satellites is higher and higher, because there are many more things that it can be a satellite of.
Right.
Right? And which makes a heck of a lot of sense. And so then what I worry about a little bit is the real observation here is we've got gas that's at relatively high velocity compared with essentially the halo velocity of that you infer for that galaxy. But that high velocity gas might have a different interpretation if a larger fraction of those are satellites. And so do you have a constraint? Yeah, so do you have a constraint on whether your galaxies are satellites or sectors?
We tried our best to ensure that these galaxies were isolated. We made sure that on the image that there was no other galaxy of similar redshift within 5,000 kilometers per second.
How big is your image on the
So it's a quick two image. So the criterion was there's no other galaxy within 600 kiloparsecs, as far as we could tell, and not within 5,000 kilometers per second in velocity.
So early on in talk, you showed that you had 2D information relative to the galaxy major axis and minor axis. Is there any correlation between, if we accept that all the really high velocity delta V's are outflowing gas, was there any correlation that is outflows coming along the minor axis or the major axis or somewhere in between? Or you
There was no correlation. Most likely we don't have enough to be able to pull it out, but also there's only the two highest condensation absorbers are aligned, but the rest are kind of random. So there's very little alignment information. I'm thinking that's just the way H1 tends to be more associated with, could be associated with other things too. Like I said, the escaping clouds are most likely outflowing. We don't have a huge constraint on not on the bound clouds.